Okay.
So whenever you're ready, I think.
Okay. So hi everyone, and today we're going to talk a little bit about grammatical picture generation, and actually just to show what I think are the most illustrative introductory examples to the topic. But first, just to be sure that we are all on the same page, I want to check what is a formal grammar. So formal grammar, so before defining what a formal grammar is, we need to define an alphabet. And an alphabet is just a finite set of symbols. For example, this that you see on the screen is an alphabet of 3 symbols, A, B, and C. And symbols are just abstract concepts. They can be whatever we want them to be. Then we need to define what's a string, and a string is a finite sequence of symbols. For example, if we use this alphabet that we had before, AB is just a string over this alphabet, BCAA is another string, and epsilon denotes the empty string, which is the string with no symbols. And then we define what's a language, and a language is a set that could be finite, it could be infinite, whatever we want. Is just a set of strings over an alphabet. And if we go back to this alphabet we had before, this could be a language. It could be A, AAB, AAB. And if V is an alphabet, V asterisk represents all the strings over V, including the empty string. Now, a grammar formally is a tuple that contains an alphabet of non-terminal symbols, which are symbols that we're going to replace. Also an alphabet of terminal symbols, a set of productions, which is defined by this pretty weird expression that just means that each production is a tuple of 2 elements. It's an ordered pair in which the left or the first element is just a sequence of terminal and non-terminal symbols containing at least one non-terminal symbol, and the right part or the second part is just a string of terminal and non-terminal symbols that could be empty. And finally, we have a starting symbol. Now, how this very abstract concept generates strings? Well, here you have an example. In this example, you can see that we have a set of only one non-terminal symbol. We have 2 terminal symbols, A and B, and we have these productions. Now, in this way, it's quite hard to read them. So it's usually to denote them like this, using an arrow. And also, if they share the same left bar, they are grouped together using the bar to denote different alternatives for the same left part. And then with this grammar, we can generate a string like this. We start by the starting symbol, of course, and then we find in the current string, which is in this case only the starting symbol, we find any occurrence of the left part of any production, and then we replace this left part by the right part, and we obtain a new string. For example, here we have S, and S could be replaced by AS according to the production we see on the string, and then S becomes AS. If we continue like this, we can again replace the left part of the productions, and we keep obtaining strings, and then we continue this process until we cannot apply any other production to the string we are constructing. And if we end up with a string containing only terminal symbols, then we have generated a string. And this is how grammars work. There's a big theory around formal grammar, formal languages, and there's of course a classification for them. And in this case, if the left part of all production is only a non-terminal symbol, then the grammar is classified as a context-free grammar. This will make sense after. But you can see that grammars are good generating strings of symbols. But how can we make them generate pictures? Well, we need to adapt them. So for instance, we can change the nature of strings. So far, these strings are just unidimensional things. So we can try to generate bidimensional things or bidimensional arrays so we can generate an image. Or we can also change the nature of the symbols. Symbols are abstract, but we can give them meaning. So for example, the symbol A could represent a shape, an hexagon, and we can also, since they are something concrete now, they are shape, we can use the shape properties in our advantage. Or we can interpret the symbols on the string, like for example, drawing commands. Let's say we have UR, could be just draw a line up, and R just draw a line to the right. And in this way, we can interpret the string and get a picture out of it. And then we can, using a grammar, we can generate the string, and then from the string, interpreting the string, we can generate a picture. So let's see some examples on how this can be done. The first examples are array grammars. These are grammars pretty much similar to what we had before with the traditional grammars, but in this case, they are meant to generate bidimensional strings or arrays. And the productions now encode the spatial position of the elements. So for example, here at the bottom, you have an example of what a production in these grammars looks like. You have A on top of B, and this produces A on top of C, which means that in the array we are generating, whenever we find A and B below, we can replace this B by a C. So let's see a more concrete example. Here we have a grammar which has a definition pretty similar to the one in the first example. Then we have this bunch of productions, and then we have these productions that somehow encode that whenever we find a 1 and below a B, we can put in the place of a B a 0. Or if we have a 0 and then a B, we can put a 1. So how do these grammars work? First, we have an array, a bidimensional array, with the starting symbol in the middle. This B is a special non-terminal symbol representing a blank space. So now we can apply the productions. For example, we have S produces 1, so we replace S by 1. Then we can use the other production. So for example, 1 with a blank space by its size becomes 1, 0, like this here. And then we can continue with a 1 and below a blank space, we can put a 0 there. And like this, we can fill the entire array. And if we interpret accordingly this array, then we have a checkerboard pattern. But these primitives that array grammars work with are really low level, almost at the pixel level, if you want. So it's not uncommon to merge more than one array grammar to get more complex patterns. So for example, here you have this grammar that fills an array with A's, and then with this other grammar, when we finish with the first one, using the second one, we can generate a different pattern starting from the A and generating new arrays. So the way it will work is that we start again with the array with the starting symbol in the middle and everything blank. Then we fill it with A using the first grammar, and then each A is translated using now the second grammar, and we obtain something like this, that if we interpret accordingly, then we obtain a cute pattern like this one. So, but again, these primitives are still pretty low level, and that's why we have shape grammars. So shape grammars differ a little bit from the traditional grammars in the sense that the symbols are now shapes. And whenever we have a string, we have a combination of shapes. So for example, we also have terminal shapes, which are shapes that are not going to change. We have markers, which are somehow a parallel to non-terminal symbols, and these markers are going to tell us that we haven't finished generating the shape. And then we have a combination of markers and terminals that's calling the starting shape, which is something similar to the starting symbol we had before. And the productions are quite similar to a traditional grammar, but in the left part, we have a combination of terminal markers containing at least one marker, and in the right part, we have a combination of shapes like this. So this grammar will start by the starting shape, of course, and then we'll find the left part of any production in the current shape. Now, this part could be transformed, could be, for example, translated or scaled or rotated. So we have to consider all these possible operations, then find the left part, transform the left part to match exactly what we have in the current figure and transform also the right part and replace the left part by the right part. It's something like this. For example, we start with the starting shape with the first production. We can now obtain this picture. You see now that the dot, the marker, is rotated, so we need to rotate also the production, and we obtain something like this, and we can continue on, and we obtain with this specific shape grammar, we can obtain a honeycomb pattern like this. So, but so far we have seen a way to transform the strings and to obtain something with 2 dimensions, and we can see also how to use different kind of symbols. But what about if we interpret the strings as drawing commands? Let's use, for example, this simple approach. If we have a symbol U, then it's a line up, then D is a line down, left, a line to the left, and then to the right. These are, now I realize that these are interchanged, but it doesn't matter, you get the idea. And now we have ULDR, this represents a square, because we go up, then to the left, then down, then to the right, with the changing L by R. So what we can do with this? Well, we can go back to the traditional grammars and do something with them. Use only these symbols, we can generate drawings. So for example, here we have this grammar with non-terminals S and B, and using as terminals these 4 symbols we had before. And this is a very, very simple context-free grammar that can generate strings like this, UR, GR. This represents this drawing, go up, go R, go down, go to the right. Now, this specific grammar is called, it's able to generate drawings called Manhattan skylines, because they are able to generate curves like this that resembles the landscape of Manhattan somehow, with skyscrapers and buildings and all that. We can do something more sophisticated. So for example, this second grammar has a little bit more production and is able to generate drawings like this that can represent, if we are abstract enough, they can represent trees. And you can see them with this production. For example, the tree start with going up, and then here L and R represent the branches of a tree. With R, we can go R, we can go, first of all, with left, we can go left, up, then down, and to the right, and in this way we can draw branches. And if we let this grammar generate more strings, we can obtain beautiful abstract trees, just like this one. But in the same spirit of using context-free grammars to generate drawing, there's a software I really like, and I brought to you today. It's called context-free art, which is a software that generates a picture using context-free grammars. In these grammars in particular, the symbols, the terminal symbols, are shaped, and we can define our own shapes, and then it has its own DSL to specify a grammar and generate shapes, and it also has some way to control randomness. And in fact, it's not just context-free grammars, but they encoded attribute grammars, which are grammars as before, but they add attributes to the symbols and semantic rules to specify the way the information passes from one symbol to another. So let's see an example. So here, I have defined shape. A shape is like a non-terminal symbol, and then these ones are the terminal symbols. For example, square is a terminal symbol that represents the square, and circle is a terminal symbol that represents a circle. And we can use these attributes to specify, for example, the position and the color of these terminal symbols to affect them. For example, in this case, the circle has been colored with a kind of a light blue and has been positioned to the side of the square. But context-free lets us define our own primitives, our own terminal symbols. For example, this is a definition of a new path that resembles somehow a leaf, using some well-known controls, drawing controls like move to this position, draw a line here, draw a line there, and of course we can use again attributes to modify how these symbols look when they are drawn. In this case, it has been modified to be green. Now, context-free art goes a little bit beyond grammars and let us use some structure, some controls and structures. So, for example, we can have loops, we can have conditionals, and we can have also functions. In this example I'm showing here, you can see that we use a loop to draw 100 leaves and use a function, a predefined function random, to randomly position all these leaves in the canvas. And they are also like units. So every grammar definition is like a unit from which we can import our elements. So here, for example, I'm importing the primitive from the previous example that you can see. And now, of course, you can generate other things, and these are especially well fitted to generate trees, because trees are kind of a context-free structure. See, for example, here we have a non-terminal tree that puts a square, then two branches, and then a tree. And a branch is just a tree or nothing. And here you can see that we added a number on top of a rule, and this means that we can add probabilities to the rules from the way they are being picked to generate the figures. And this is an application of stochastic grammars to drawing. So context-free is a really nice software. It's available for free out there, and these are, for example, this is what we're seeing now. It's actually context-free, and the examples I had in the slides. So here's the example of the square and the circle. And also, we have this example of a custom primitive. Then you have the example of this collage I made before, and you can have a random picture every time you run it, but you can also control the seed of the pseudo-random number generator, which is pretty cool. And also, you can have the tree grammar, and you can render as many trees as you want. And you can render a forest if you want with very different trees, yet they are all similar. So context-free has a community around it, and there is a gallery. Here you have the link where you can find true masterpieces. So for example, these are just examples from the first 2 pages of pieces people have posted in this gallery. And now we go into the last approach I wanted to share today, which are L systems. L systems are kind of similar to grammars. They were proposed in the 68 by Lindenmayer, and they work like this. So first, they have the notion of constants and variable symbols as opposition to non-terminal and terminal. They start, instead of starting by a non-terminal symbol, they start by a string of symbols, constants or variables, which is called an action. And then we have rules in the same way we had them before, but the difference is that the rules are applied all in parallel. So how does it work? Let's say we have this L system, which has an axiom, just V. V produces A produces AB. Let's see how it works. So first, if we do nothing, we obtain the axiom, which is the starting string. Then we replace all the symbols. In the first iteration, we replace all the symbols. And in this case, we have to replace B by A according to the production, and we obtain A. Then A has to be replaced by AB. And then we have to replace at the same time A and B. A is replaced by AB, and B by A. And the process goes on and on. So in one iteration, you have to replace all the variable symbols and replace them by the same symbol has to be replaced by using the same production. And you can obtain a string. Now, if you have been a bit picky, you can note that the length of the strings, of these strings that have been generated, the order, that matches the Fibonacci sequence. And it's actually this L system is able to generate strings whose length matches the Fibonacci sequence. We have 1, 1, 2, 3, 5, 8. This is actually the first example proposed by Lindenmayer. So L system can be combined with turtle graphics to obtain pictures. What are turtle graphics? Well, they are drawing primitives that come from the Logo program, which from the Logo language, which is a small programming language that is being used to teach kids to program. And they have the following primitive. So forward moves the turtle, the cursor, forward and draws a line, then minus rotates the turtle, plus rotates the turtle, and the turtle also has a stack of memory where it can push and pop the state of a turtle, which is the position and the rotation. With an open bracket, we push the state, the current state of a turtle. With pop, with a closed bracket, we pop the state on the top of a stack and make it the current state of a turtle. So how can we merge these two things, L systems and turtle graphics? Well, we can have something like this. The action is F minus F minus F minus F, and we have only one production. F produces that big string you have there. And then we are going to tell our turtle that whenever it rotates, it will use a 90-degree angle. So let's start generating something with it and interpreting the turtle graphics. So first, this is the action. This is how the action looks like. You go further, then you rotate, further, rotate, and you obtain a square. Then each F is replaced by another string, and you obtain something like this. And if you continue, well, you obtain a fractal, which is called the Koch Island, if I'm not mistaken. And this is the way you can leverage L systems with turtle graphics to generate pictures. Let's see another example. This is called the round curve. It has two productions with X and Y. In this case, we ignore X and Y from when we interpret the string we obtain, and we start by this, only very little forward movement. And then as we continue, the drawing gets more complicated and more complicated until we obtain something like this, and we can, of course, go on until we want to. And if we use this stack, then it's very handy to generate trees. And you have here two examples with a variation of the angles to obtain different trees, and they can look pretty natural. They can look pretty good. So, but so far, an image, a picture, is a string generated by a grammar. But what if we encode an entire language in an image? Let's do one thing. Let's say we have this image and we divide it in 4. And to each one of these quadrants, we assign this number. And then we do the same for each quadrant. And we obtain now, assigning a number in the second place for each quadrant, we obtain a 2-symbol string for each square here, for 2, 2, 2, 0, 0, 0. And we can continue until the level we want. So here you have 3 symbols for each square. Then now each pixel in an image becomes a string, and the image, the entire image, can become a language. So let's say that we have this regular expression. And this regular expression, what it means is that we have a string where no 3 is in it. It's only 0, 1, or 2. Then if we start drawing this, putting in black each string that belongs to this language that is matched by this regular expression, we can obtain another cute fractal. And like this, we can even leverage regular automatons to generate or to represent cute images like this one. But this is a topic for another coffee, I believe. So of course, what I have presented here is just the tip of the iceberg. So now I want to give you some pointers to where to find more information. And these are the books where I took these examples from. The first one is Grammatical Picture Generation, a very nice and formal book. Then you have also Recent Advances in Formal Languages and Applications, in which just one of the applications is to generate drawings and to operate over images using formal grammars and automatons. And then you have the Handbook of Formal Grammars, the volume 3, that's called Beyond Words. and they just don't just go into a topic of images. They go a bit far. And then there is the beautiful book, The Algorithmic Beauty of Plants, with plenty of examples, and they explain how to extend all the concept of Bell system to generate 3D natural looking and real looking trees. This is an observable notebook where I have all the notes from the presentation. You can see the same examples there. And it's also interactive. So you can do your drawings, generate your strings. And do the same with the L systems, which are below. And we can have the trees grow. And we have, there you can see more examples of how to generate cute fractals with L systems. So this is it. As I told you, it's a very brief presentation with only very introductory examples that you can see, and you can use this book site at the end of the presentation to expand and dig deeper into this amazing topic of grammatical texture generation.
Thanks a lot.
You're welcome.
I will have a first provocative question,
okay,
if it's possible. Do you know if it's because I really play a lot with such kind of stuff when I'm learning recursivity or when I'm learning functional programming? But after, I'm still wonder in which context it really applies. So do you know if some, I don't know, gaming stuff using such kind of representation?
Yeah.
Or,
I mean, have you seen any Pixar film?
Yeah.
Yeah, most of them uses. There are actually plugins for 3D Max, which is the 3D modeling language, and all these L systems have been ported there, and you can use them to generate trees. And most of the trees in these plugins have been generated using L system. If you go to this book, The Algorithmic Beauty of Plants, they present this kind of things there. So,
but it's mainly for tree. Or could we represent also cloud or some water animation? I don't know.
Well, I don't know about water, but cloud animations I've seen, and also I've seen ways of generating different places using this kind of thing. But of course, tree they fall natural into this idea. So actually, Lindenmayer, what he was doing was modeling somehow how the plants grow using the L system. So that's why they really fit the purpose of drawing images. And there are also theory in terms of how plants grow and how they grow old too. So there's I recommend you to read this book, and this book you will have pointers to actual uses.
And do you think we could also find some application for managing the scalability of a microservices system in following, I don't know, such kind of, I'm really thinking about other place where we could use such kind of, diagram representation, generation, etc. So have you also seen other?
I don't really know. As I said in the beginning, it was only for pictures, but I suppose they can be leveraged to do whatever. I mean, grammars, they are used to fuzz software in testing, for example.
Okay.
So you have a grammar for the input, and you can use it to generate near close. The inputs are close to being right, or whatever. Grammars can be used to generate many things. I've seen applications to sound generation too. So they can be really helpful.
Really, thanks a lot.
Yeah.
So any other question?
This is Benoit. Yeah, go ahead.
Okay. Is there a way to express hidden constraint, like you show some Manhattan drawing, and in Manhattan drawing you can go under the ground. So there is some schema that you cannot apply. So is there a way in your software to express some constraint?
Well, yeah, sure. I mean, you can. The context-free has it's a full DSL with loops and conditionals. You can define your own functions as well. So yeah, of course, you can do something like the tree cannot grow beyond this space, and you can do it.
Okay, but in the program, and you can do it in the grammar.
Ah, okay. You mean in the examples it show with the L systems?
Because if you say in the grammar you can't do this and it's respect some aesthetic rule, it's very powerful, right?
Okay, but then you go into the realm of attributed grammars and the way, which is what I was saying. So you put some rules on how to modify the generation of the symbols somehow, and you pass some information to them to constrain. Of course, you can do. It's not done in these examples. These are really simple examples meant to generate whatever string that comes out of it. But of course, you can do. For example, you can try to restrict branches to go beyond a certain level, or things like that. I mean, you can do whatever you want. Just the grammar gives you a way to organize the generation of your string, and then the way you interpret the string is up to you.
Okay, thanks.
Yeah, thank you so much, Oscar, for this presentation. It's absolutely mind-blowing. And I have a question about, it's basically using grammars as a domain-specific language for expressing the generation of arts. And I'm just wondering if there is a specific property from grammars beyond any logical languages. We can think about Prolog and so on, or any graph transformation languages, or even just imperative languages such as Logo and so on. So there is many domain-specific languages that can be think of for generating such kind of things. And I'm just wondering if there is a specific property in grammars for having a whole community. I'm just discovering this community. It's just amazing. And so
I'm not truly aware of that. I would say that depending on the type of the grammar, you're going to be more expressive or less expressive, and you're going to be able to generate certain pictures in a way or not. So for example, we know that following the hierarchy of grammars, regular grammars are the most restricted, then context-free, then context-dependent, then unrestricted grammar. So maybe changing the type of grammar will kind of change the type of picture you can generate and the expressiveness of what you can generate. This is what I believe. But other than that, I'm not sure.
Okay. Interesting. Okay, thank you so much.
Thank you.
Yeah, it's Mathieu. So thank you for your talk. It's a shame that I haven't you as an instructor on formal languages courses because we have we add all courses about this stuff, but presenting like that, it can be more inspiring for students. So I think you should talk with people at University of Rennes that teaches formal languages. I'm not sure they present some art like that. It's a very nice perspective on this. And
wow, I really would like to talk to them, because this is a class I used to teach in Cuba, actually, in a formal language course, and then we had one class for this kind of thing.
Yeah. So yeah, you should talk with these people, because it's less abstract, I would say, to present formal language like that. And very interesting.
I think about Olivier Ridou. You should talk with Olivier Ridou. He is very smart and very open-minded, and he's the one that teach some courses about formal languages at Rennes 1.
Okay, thank you.
Yeah, yeah, that's definitely. Yeah, I was wondering. When you design a program for generating art, what seems hard to me is to have an almost good solution, but it's not really what you want, and so then you have to debug your program. And here, for me, it's very difficult because it's like debugging a regular expression. Okay, it's nice in theory, it's very concise, but then when you have to find what's going bad, it's kind of hard. And I think it's also related to what Luc said, is that sometimes you have some constraint in mind, but in your program you don't express it because it's not that easy to express it. So I'm wondering, are you aware of works that try to assist programmer to debug your programs and stuff like that?
I'm not aware of that. I'm not sure.
It's tries and errors, right?
Yeah, mostly trial and error. So the one I've used most in the past is the P5. I think you tweeted about it some days ago. Yeah. And I really like P5 for this kind of things and generating random pictures and random figures all over the place. And the only way I've seen to do it is just trial and error and debugging JavaScript. But it can be tricky, as you say. Most of these rely on randomness at some point, and it's really hard to get it right.
Yeah, exactly. And yeah, I was also wondering if there is any chance to reverse engineer a formal language out of an image.
Well, I believe there are works on that.
Okay.
I believe there are works on that, and there are very, very interesting things on that. So, for example, here I've shown at the end only an automaton that, well, the string belongs or doesn't to the language. So you have a black dot or a white dot, but there's a theory beyond that to generate colors and how you combine them to generate new colors. So this one of the books I put in last in the presentation is about this, how to encode picture operations and even fractal generation using finite state machines. So there is a bit of work on that, and also the reverse, how from the image try to infer something.
Okay, thank you very much.
So any other question, comment? Please go to this notebook and play with it and let me know your thoughts. It's published in this Observable. Observable is also a very nice platform for visualization, and maybe we can do June another coffee presenting on Observable and how it compares to Jupyter Python notebooks, which there are differences among them.
For example, that would be great, yeah.
But not for next week, okay?
Yeah, no problem.
But for example, you were asking the other day, and Flip, how to make your notebook interactive, and Observable was built with this goal in mind. So how to make them actually interactive first. So it's really easy to do this kind of thing. So maybe we can do a coffee about this.
Yeah, actually, I was trying. I want to test it to see if it's possible to do that interaction with how to say maps. Of landscapes and so on. So I'm trying to do it at the moment, but I haven't tested it fully yet. But yeah, it seems really great.
Yeah, it's built with this purpose, and you can find pretty cool visualizations of maps which are interactive and which you can select things in the map and all that. So it's really nice. It's a really nice system for that.
So, well, thank you a lot, Oscar, because it was a really nice presentation. I think
thank you.
A new topic to discover.
Indeed, it's a very interesting topic, and this is just a very few introductory examples. So there is much more, a lot more of this.
I'm not sure, Oscar, that we all have the URL of the notebook. Can you send it to us?
You probably none of you probably have it because I haven't shared it. So it's a very nice way to say it.
Excellent.
So let me share the URL. I will share it through the chat.
Great.
Thank you so much.
Nice, thank you.
Welcome. Welcome.
Cool. Well,
And maybe just a question about observable. Do you know if it's pluggable like Jupyter, such as we can add kernels and so on in Jupyter? Do you know
Well,
if
actually,
it's the same architecture? Or?
yeah, not quite the same, but each notebook in Observable becomes a library, so you can import things from our notebooks. So you can build on top of them and do more things. So this is something I actually do in this notebook in particular. I grab some input controls from our notebooks to use them.
Okay, looking forward to your next coffee about this.
Okay, thank you.
well, if no one has some questions or comments, I think we can close the presentation.
Maybe can we share the video on the YouTube channel?
Oh, maybe.
Okay.
Uh,
I will send the file to Oscar and then he will decide to do whatever he wants.
Okay, thank
Okay.
you.
Yeah.
By the way, I'm adding the YouTube section to the website, so a page where we have all the
Nice.
videos.
Excellent.
Great.
And we need your video. Okay.
Okay. Okay, so well, thank you so much for listening.
Thank you
Thanks,
so much
that
for-
was very well explained. And
Yes.
Yeah.
see you.
Thank you so much.
Thank you.
Bye. Take care.
Bye bye.
Bye.
Ciao.
Yeah. See you next time.
Ciao.